NHANG survey estimated dietary intake of 10 key ingredients. Calcium for adults 60 years or older, they found the mean daily intake of 721 milligrams, a standard deviation of 554 milligrams. Compute the probability that a single randomly chosen adult over 60 years old will have a daily calcium intake of under 400 milligrams. Now, how would I solve that problem? What do we know there? They gave us the population mean, right? Right? Did they say what the sample size was? No, they gave us the population mean, 721. They gave us a standard deviation for that population of 554. Now, if we're going to calculate the probability, if we assume that that's the population mean and population standard deviation, then we're just dealing with the normal distribution. We're going to calculate a z-score and see what percentage of these outcomes that we would expect to be under 400. Over 400, so on and so forth. If you took a random sample of size 50 from this very large survey, right, compute the standard error and find the probability that the sample mean will be greater than 800 milligrams. Okay, so our sample size is 50. We know we assume that because it's such a large sample, we're going to use 454 as the population standard deviation. We're going to use 721 as the population mean, right? So, but we want to know the probability of getting a sample of size 50 that will that's greater than 800. So, what do I expect? What's the mean that I would expect to get when I take a sample? I would expect to get a mean of 721. That's my mu. Okay. Instead, I'm saying, what's the probability of getting a mean greater than 800? Well, now I have to see how many standard deviations apart that 721 and 800 are. Okay. So now the only problem is that in this survey, mu was equal to 721. Sigma, because it's such a gigantic survey, was 454, I think. Right? So now I'm going to take a sample of size 60, was it? 50. I'm going to take a sample of size 50. Okay. And I'm going to say, what's the likelihood that X bar is greater than 800? Okay. So now, if I were looking for a single random individual in this population, I would use the Z table. I would just calculate, well, let's see, 721 minus 800 minus 721, right, over the standard deviation, 454, calculate a number of standard deviations, see what area of the normal distribution is above that level. But now I'm dealing with a sample. And the sample has this, we expect it to have approximately the same value as the mean of the population, but I'm looking to see how often I would get a sample how often I would get a sample, what percentage of time I would get a sample that's bigger than 800. So now I need to know how variable would be samples of size 50. So now I need to calculate my standard error because I'm dealing with samples of size 50, right? That's going to be equal to standard deviation over the square root of the sample size, right? That's equal to 454 over the square root of 50 is equal to, let's give that a try. Okay, square root of 50 is 0.707. Okay, and 454 divided by that is going to be equal to 64. I'm just going to call it 64. Okay, so what percentage of these samples would I expect to be above 800? Well, let's see. This is my distribution of samples that I would expect. I would expect the mean to be 721. How often would I get a sample above 800? So I'm looking for this area up here. Well, that area, the z-score for that area is going to be equal to, let's see, 64. It's going to be equal to 721 minus 800 minus 721 over 64, okay, which is equal to 79 over 64 is equal to, let's see what that comes out to. $1.23. So if I go to my Z table, okay, let's see, Z-score of, what was it again? Left it on my calculator, I hope. 1.23, good. 1.23. Z-score of 1.23. 1.20123 represents an area of 89%. But that area of 89% is which side of that 0.800? It's below it. We're interested in likelihood of getting a sample with a mean of 800 or above. So we're actually looking at 11% or 0.11 probability of getting an outcome that high from a sample size of 50. Okay, so you have to think about, am I dealing with a population in a Z table? Am I dealing with a very large sample or situation where I know the population standard deviation, Z table again, or am I dealing with a small sample where I have to deal with the t distribution instead? Okay, so let me just see what else I can go over here. I just wanted to point out there's another situation where you might wind up with dealing with proportions. And that is, for instance, let me try and recall an example we just went through here. Okay, let's say 30% of the population is left-handed. You go out and you sample 100 people, okay, and you sample 100 people, and you find PCAP, you find that 30% of that population is left-handed. In other words, you found that 30 out of 100 people are left-handed. Okay? So now let's say you're not going to look at this as a proportion, but you're going to look at it as the number of people out of 100. Okay? So if I sampled another 100 people, maybe I got 31 people that are left-handed. Did it again, maybe I got 28. Did it again, maybe I got 35. I'm going to take these results, instead of the proportion, I'm going to take the results for the number of people in that sample of 100 that are left-handed, and I'm going to make up a new distribution for a sample size n equals 100. What would be the middle, the point value for the middle of this, do you think? 30%, 100 people? What do you think would be the middle? 30, right? You think the mean, what would be the point value, basically the mean, would be 30 out of 100, right? If this were a sample of 100 people. Sometimes if I took a sample, it would be higher. Sometimes if I took a sample, I'd get fewer than 30. Okay, how can I get that 30, that point value? I can get it by multiplying n times p. That's my point value. So if I gave you another population, another situation where I said, well, out of every 100 people, 10 people are redheads, right? What would be, well, how would you calculate what the point value would be for redheads in that population? Well, it's 10%, right? If you take a sample size of 100, it's going to be 100 times 10%. It's going to be 10. It's going to be n times p again. What if I change the sample size? What if I go back to my 30 out of 100, my 30%, and tell you, oh, the sample size this time is 200. So what would be the middle value that I would expect for the number of people that are left-handed now that the sample size is 200? Well, it's 200 times 0.3 is going to be 60 instead of 30. So I can use this, I can describe this distribution as a specific number of people within that sample size or a proportion. When we did it as a proportion, we saw that p cap represented the proportion, and the standard error was represented by the square root of p times 1 minus p over n. Well, this time our standard error is going to be equal to the square root of n times p times 1 minus p. Right? So you can do the same thing with this that you did before with the other proportion. So what's my standard error going to be? It's going to be equal to the square root of 100 times 0.3 times 0.7, right? Okay, that's equal to 21, but I got to find the square root of it. So it's equal to about 4.6. So standard error is equal to about 4.6. Okay, so what can we do with that now? Well, now we can find the confidence interval for this point value. So we can say 30 plus or minus 1.96 times 4.6. In other words, in that case, basically we have a 95% confidence interval that if we took a sample of 100 people, that the true, if this 30, if we didn't know this 30 was a true proportion, and it was just our first sample of size 100, we found 30, then we would say that our 95% confidence interval for the actual number of people that represent that point estimate, that middle value, is going to be between, say, 20 and 40. Okay, roughly 20 and 40, two times 4.6, or actually 21 and 39, roughly. Okay, so you see how it's a little bit of a twist on the proportion from before? I don't think you'll see too much of this. I just wanted to bring it up in case it comes up. You'll see more of the actual proportion itself, because you use a lot of that. You use a lot of it in, polls and stuff like that. You use a lot of that in comparing the performance. Use a lot of it in comparing a number of different issues that might be described as binomials. Okay, so now let me see what I can do with the remaining time that I have on my battery. And I'm going to open up homework number 4B, just so we get a little taste of it. How are you guys doing online? Oh, yeah, 12. Good work. Well, this is embarrassing. What happened? I should open up Blackboard. Try again. Okay. Okay, just to prep you guys for next week. And it will indeed actually be. I didn't realize it was the same night as class night. Halloween. Okay, let's take a look at this first problem. Okay, let's see. Primary zombie food source is high in protein and fat, low in carbohydrates. Okay, so serum cholesterol levels are measured at on 25 randomly selected zombies. The mean sample turned out to be 151. The population standard deviation, assuming we know it, the population standard deviation is assumed to be 38. So we know sigma, and we have a small sample size, but we know sigma. We're assuming it to be a normally distributed value. So if we want to calculate a standard error and a confidence interval, we're going to use sigma divided by the square root of n, like our sample size, and we're going to use 1.96 for our 50 for our confidence interval. Now, if we don't know, let's see, and you can also do the same thing with 99 and so on and so forth. If we don't know the standard deviation of the population, let's take a look at question 8. Repeat the above study for zombie cholesterol, right? Same mean, 151.4. The sample standard deviation is equal to 38, and the sample size is 25. Calculate the standard error and the confidence interval. So I'm going to do that right now. Okay, I'm not going to need this. Pull up my sheet here. Here we go. And let me copy over these values. Okay, let's put in these values. They are our X bar. Our sample mean is equal to 151.4. Our standard deviation for our sample is equal to 38. And our sample size is equal to 25. So our standard error, instead of using sigma over the square root of n, we're going to calculate it using the standard deviation from the sample over the square root of 25 or 5. So that's going to be equal to 7.6, I guess, right? Okay, tell me now, or forever hold your peace. Okay. Now calculate, that's our standard error. And we calculate it using the standard deviation of the sample. Okay, and it's a relatively small sample size. So we know we're going to need to use the t table. Okay, so now let's calculate our confidence interval. 151.4 plus or minus the value for t that we're going to use, right, which is 0.95 for a two-sided, right, times 7.6, our standard error. Now let's look that up. Now, what is that? It's going to be, how many degrees of freedom is that going to be? Yeah, there we go. Okay. Okay. Here's our t-table. 24 degrees of freedom. Okay, for a 95% confidence interval. Instead of using 1.96, because we are working with standard deviation of population of the sample, we're going to use 2.064, right? 2.064. So I'll go back here. So our confidence interval is going to be 151.4 plus or minus 2.064 times 7.6. And I'll leave that for you guys to work out. Calculate your margin of error, add and subtract it at that 151.4. Okay. So it's pretty simple. It's really parsing this so you understand whether you're working with population mean, standard deviation, when you're working with your sample, whether or not you can apply the z-score or the t-score, what t-score to choose, and so on. And then there's just the basic formulas you're using over and over again. The proportion formulas are a little bit different for calculating the standard error because you're working with proportions. But if you work basically from the formulas, you shouldn't have too much